Welcome to another episode of My Weird Prompts, an AI-generated podcast featuring the random prompts of Daniel Rosehill as answered by a revolving cast of friendly AI characters. Join us for deep dives into AI, technology, and whatever other random thing Daniel finds fascinating today. Subscribe on Spotify or your favorite podcatcher. Now, today's episode.
This episode was generated using artificial intelligence. Please verify facts.
Hello, Herman and Corn. So we have chatted in a number of episodes about automation and AI agents, very topical, of course. And I was looking at the production pipeline in Modal and making some edits yesterday because some of the episodes were not generating, and it was the runtime restriction or the cutoff was chopping it. So I just made some adjustments to that, and now it's back to working. So it's running on Modal, which is a great serverless GPU platform that has been immensely helpful. In fact, this podcast would not be possible without it financially, because it's so much more affordable than using APIs to use Chatterbox. So it's a brilliant tool, and it does these persistent. You can run persistent Python jobs like these 20-minute generation scripts, during which the audio is running, it's being concatenated, it's being published. The whole shebang occurs in those 20 minutes. But the start of it is this webhook call that I send my voice prompt to using a form. It hits a webhook, and that triggers the pipeline. It's a pretty classic automation setup. Now I'm wondering, Herman and Corn, when I've used these platforms like N8N, and as much as I really love N8N, quickly realized that it can be quite a limited tool in the sense that it's an abstraction over code, and there's many things that you can't do because it's an abstraction over code. So you can get a lot more flexibility if you just remove that layer. Of course, the flip side of that is you've got more complexity. You don't have that visual programming language anymore. But one thing that is relevant when we're talking about running automation boxes on persistent hardware, so we're not talking about serverless, we're talking about hardware that a classic server like a VPS or an AWS EC2 instance. And in order to do something like this production pipeline, you'd need to stand up the webhook, because the platform isn't going to be providing that for you. So a webhook has to be always on, unless you want it to be, because that's what a webhook does and makes it different than a cron job or a service that polls periodically. So my question, Herman and Corn, when we're scoping out compute and looking at how much these things will cost, that process of having webhooks that might be listening for, let's say it's even one webhook listener, and that's the start of the pipeline. How much compute is actually involved in that? Because I know the answer is absolutely nothing, or in practical terms, it's virtually nothing. It's tiny amount of resource usage. That's not going to be your cost driver. But it still makes me just wonder how that's possible at the technical level. Because if I was trying to explain how the pipeline works to a friend who was maybe less technically inclined, you might say, well, I have a server, and the server is always listening for anything I send it to. It doesn't matter if I send it at 2 a.m. or 5 a.m. or 3 p.m, but the very second, and not later than that, it's not waiting, there's no delay, it's instantaneous. Maybe it's just me, but I would say, oh wow, that sounds like that's really impressive. That must be like, you must need a whole computer for that. And the answer is no, you just need a webhook listener, and you can do this for $1 a month. So my question, Herman and Corn, I hope I'm making clear what I'm trying to get at here. We know that the actual agents involve some computation, of course, running the models do as well, but we've evolved to this point where the actual 24/7 listening to the internet thing effectively just requires standby battery. How have we managed to get to that? And if we did want to actually calculate the resources, what are we talking about for just standing up the first part of a fully owned persistent automation instance? Over to you two.
Hey everyone, welcome back to My Weird Prompts. We are coming to you from a very sunny afternoon here in Jerusalem. It is February 18th, 2026, and the light hitting the stone walls outside the studio is just incredible today. I am Corn, and I am joined as always by my brother, the man who probably has more browser tabs open than there are stars in the visible sky.
Herman Poppleberry here and ready to dive into the deep end of the stack. And, for the record, Corn, I have actually moved most of my research into a local vector database now, so my tab count is down to a very manageable 45.
Only 45? You seem especially caffeinated today, Herman. What have you been reading that has you this energized?
Oh, just some light reading on kernel-level networking, asynchronous input-output patterns, and the latest benchmarks for IOUing on the 6.12 Linux kernel, the usual stuff that keeps a Poppleberry up at night.
That is actually perfect timing, because today's prompt from Daniel is right in that neighborhood. Daniel sent us a message about his automation pipelines. He has been using a platform called Modal to trigger AI agents for his voice-to-text and analysis workflow. He noticed something that felt like a glitch in the matrix. He saw that while the AI part, the actual inference, is obviously super heavy on computation and costs him money, the initial part, the webhook that is just sitting there waiting for a trigger, seems to cost almost nothing. It is always on, always listening, but it is not burning through its credits or resources.
It is a classic architectural question that gets to the heart of how we build the modern web. How do you maintain a persistent presence on the internet without paying a persistent price in terms of electricity and silicon? It feels like it should be expensive to be always on, right?
Exactly. Daniel was asking how this is achieved at a technical level, and what the actual resource requirements are for that first part of an automation instance. Like, if you were to stand this up yourself on a private server, what are you actually spending to have that webhook just exist? Is it a tiny flame that never goes out, or is it something else entirely?
I love this because it touches on the fundamental way modern operating systems and networks actually talk to each other. To the average user, it feels like magic. You have a URL, and at any moment, day or night, you can send a packet to it and something happens instantly. It feels like there must be a little engine idling there, burning fuel just in case a request comes by.
Right, that is the intuition. If I want a light to turn on the second I flip a switch, there has to be some tension in the system. But we know that running a simple web server or a listener isn't like keeping a car engine running at 3,000 RPMs. So, Herman, let's start with the basics. When we say a webhook is listening, what is actually happening inside the computer?
Okay, so to understand the listening part, we have to look at the concept of a socket. In the world of Unix and Linux, which is where almost all of this infrastructure lives, there is a famous saying that everything is a file. A network connection is essentially treated like a file that you can read from or write to.
So, when a program wants to hear from the outside world, it tells the operating system, "Hey, I am interested in any data that comes in on port 80 or port 43.
Precisely. The application makes a system call. Usually it is literally called listen. But here is the trick that answers Daniel's question. The application itself doesn't just sit there in a loop saying, "Is there data yet? Is there data yet? Is there data yet?" That would be polling, and that would indeed consume a lot of CPU cycles, because the processor is constantly checking the status of that file.
That is the, are we there yet, approach to networking. We have all been on that road trip, and it is exhausting for everyone involved.
Right, and it is terribly inefficient for a computer. Instead, what happens is the application says to the operating system kernel, "I am going to sleep. Wake me up only when a packet arrives for this specific address and port."
So the listening is actually the state of being asleep? That sounds like my kind of job.
In a very real sense, yes. The process enters what we call a blocked state. It is removed from the CPU's execution queue. It is not taking up any clock cycles. It is just sitting in memory, taking up a tiny bit of space in the process table, waiting for an interrupt. The kernel is the one doing the heavy lifting of keeping track of who is waiting for what.
Okay, so let's talk about that tiny bit of space. Daniel was asking about the actual resource requirements. If I have a process that is blocked in waiting for a webhook, what is the memory footprint we are talking about in 2026?
It depends on the language and the framework, but at the kernel level, a socket structure is remarkably small. We are talking about maybe a few kilobytes of memory to store the state of that connection, the IP addresses involved, the port numbers, and the buffers. If you are using a very lightweight language like C, Rust, or Go, you could have a listener sitting there using maybe 5 to 10 megabytes of total system RAM, including the entire overhead of the runtime.
10 megabytes. That is practically nothing in the context of a modern server that might have 64 gigabytes or even 128 gigabytes of RAM.
It is a rounding error. You could literally have thousands or even tens of thousands of these listeners on a single modest machine without breaking a sweat. The real cost isn't the listening, it is the responding. But wait, I should clarify something. Even that 10 megabytes is mostly the application's own overhead. The actual kernel-level cost of watching that port is even smaller.
But wait, if the process is asleep, how does the computer know when the packet arrives? Something has to be awake to see the data coming off the wire. Is the motherboard just constantly scanning?
That is the beauty of the hardware-software interface. This is where the network interface card, or the NIC, comes in. Modern NICs are incredibly smart. When a packet hits your server, the network card sees it. It looks at the header and says, oh, this is for port 433. The hardware then triggers what is called a hardware interrupt.
An interrupt. That sounds very dramatic, like someone bursting into a room and shouting, "Stop the presses!"
It is exactly like that. It basically tells the CPU, stop whatever you are doing for a microsecond. We have data that needs to be moved from the network card into main memory. The CPU then hands control over to the kernel's interrupt handler. The kernel looks at its table of listeners, finds the process that was sleeping and waiting for that port, and moves it from the blocked queue back to the run queue.
So the listening is actually being handled by the operating system kernel, which is already running anyway to manage the clock, the disk, and everything else. We aren't adding a new worker that is constantly checking. We are just adding an entry to a list that the kernel checks whenever a packet arrives.
Exactly. It is like a concierge at a hotel. The concierge is already at the desk. You don't need to hire a new person to wait for your specific friend to arrive. You just leave a note with the concierge saying, when my friend shows up, buzz my room. You can go to sleep in your room, consuming no energy, and the concierge, who is already there helping everyone else, handles the notification.
That is a great analogy. But then, let's look at what Daniel mentioned about platforms like Modal or other serverless environments. He is sending a prompt, it hits a webhook, and then a whole pipeline starts. In his case, he is seeing that it is always on, but he is not being billed for it until it actually does something. How do these platforms manage that at scale? Because they aren't just running one server for Daniel, they're running thousands for thousands of users.
This is where we move from simple sockets to something called load balancing and ingress controllers. In a massive cloud environment, you don't actually have a separate process running for every single user's webhook. That would be a waste of resources, even if it is just 10 megabytes per user. Instead, you have a very high-performance front door.
The front door being a massive shared listener.
Right. Think of something like Nginx, Haproxy, or a specialized ingress controller written in Rust. These tools are built using something called event loops. Instead of the one thread per connection model, which was common 20 years ago and very memory intensive, they use system calls like epoll on Linux or Q on BSD.
I've heard you mention epoll before. That is the secret sauce for high concurrency, isn't it?
It really is. In the old days, if you wanted to check 1,000 connections, you had to ask the kernel about each one individually using a call called select. It was slow. With epoll, the application says to the kernel, here is a list of 10,000 connections I am interested in. Just give me the list of the ones that actually have new data since the last time I asked.
So the application just gets a list of active events. It doesn't have to sift through the silent ones.
Exactly. This allows a single process to handle tens of thousands of simultaneous webhooks with very little CPU usage. So, in a platform like Modal, they likely have a massive fleet of these ingress controllers. When a request hits daniel.modal.run/webhook, the ingress controller sees it, identifies it as belonging to Daniel's account, and then, this is the clever part, it triggers the spin-up of his specific code.
So the always-on part isn't actually his code. It is the platform's routing layer.
Right, his code is cold. It is sitting on a disk somewhere as a container image or a specialized micro VM. The routing layer is the only thing that is hot. And because that routing layer is shared across thousands of users, the cost per user is effectively zero. They only charge him when they have to provision, the actual compute to run his AI logic.
That makes a lot of sense. But Daniel also mentioned the idea of a persistent automation instance that he owns. If he were to move away from a serverless platform and just run his own Linux box, say a small virtual private server, he would be paying for that server 24/7 anyway. But he is curious about the actual resource draw. If he has a Python script running a basic Flask or Fast API server just to catch that webhook, is that going to wear out his CPU or use significant RAM?
Not at all. If you run a basic Fast API app in 2026, it might use 60 to 80 megabytes of RAM while idling, and the CPU usage will be essentially 0%. I mean, it might show up as 0.1% in your task manager just because of the background overhead of the operating system and the Python interpreter doing its own housekeeping.
So for someone like Daniel, the cost of the webhook is really just the cost of the smallest virtual machine you can buy, which these days is what, $5 a month?
Or even less. You can get nano instances for $3 a month, or even use free tier offerings from the major clouds that give you a small ARM-based instance for nothing. But here's where it gets interesting. The resource requirement isn't just about the idle time, it is about the burst. When that webhook hits, your server has to go from 0 to 60 instantly.
Right? It's the wake-up cost.
Exactly. If you're running on your own server, the process is already in RAM, so the wake-up is instantaneous. We call this a hot listener. If you're using a serverless platform, you might hit a cold start, where the platform has to find a machine, pull your container, and start it up. In 2026, platforms like Modal have gotten this down to sub 100 milliseconds using things like Firecracker micro VMs and memory snapshotting.
Memory snapshotting? That sounds like you're just taking a picture of the computer's brain and reloading it.
That is exactly what it is. They use a technology called CRIU, checkpoint restore, in user space. They start your app once, take a snapshot of its entire memory state, and save it to disk. When a webhook comes in, they just resume that memory state. It is much faster than starting a fresh Python process.
That is wild. So the always-on feeling is actually just an extremely fast resume feeling.
Precisely. Now, for Daniel's question about the actual resource requirements, let's get granular. If he ran this himself on a Raspberry Pi or a small VPS, he is looking at maybe 2 to 3 watts of power for the whole device. The actual listening part of the software is using a fraction of a milliwatt. It is the most efficient part of the entire stack.
I want to go back to the technical mechanism for a second. You mentioned epoll and queue. For our more technically minded listeners, why are these so much more efficient than the old way? What was the old way exactly?
The old way was a system call called select. With select, you would give the kernel a list of file descriptors, those files that represent your connections. The kernel would then have to walk through that entire list one by one to see if any of them had data. It was an O of N operation, meaning if you had 10,000 connections, it took 10,000 times longer than one connection.
That sounds like it would get very slow as you added more listeners.
It was a massive bottleneck. It was called the C10K problem, how to handle 10,000 concurrent connections. epoll changed the game because it made the kernel responsible for keeping track of the ready list. The application doesn't have to provide the list every time, it just registers the interest once, and then the kernel pushes events to a special queue. It turned an O of N problem into an O of 1 problem.
It's the difference between a teacher calling out every student's name to see if they have a question versus the students just raising their hands when they have one. The teacher only has to look at the hands.
Exactly. And in 2026, we have moved even beyond that with something called IOUring. This is a relatively new interface in Linux that allows the application and the kernel to share a ring buffer. The application puts a request in the buffer, and the kernel picks it up without even needing a full system call, which saves even more CPU cycles. It is the absolute peak of efficiency.
So, thinking about Daniel's setup, he's using Modal, which is a serverless GPU platform. He mentioned it's more affordable than using APIs like OpenAI directly for everything. That's an interesting point. He's essentially running his own worker nodes that only exist when they are needed. But the listener is the entry point.
Right. And what's cool about Modal specifically is how they've optimized that spin-up time. They use a lot of clever tricks with shared file systems so that your code doesn't even have to be downloaded to the worker, it is just mounted instantly. But at the end of the day, the listening part is still just a very efficient routing layer waiting for an HTTP post request.
Let's talk about the HTTP part of this. A webhook is usually just a post request, right? Why post?
Almost always. It's a standard web request where the payload is the data Daniel wants to process, in this case his voice prompt or the metadata about it. Post is used because it allows for a large body of data to be sent, unlike a GET request, which is usually just for fetching information.
So, if I'm building my own webhook listener, I'm basically just building a tiny web server that only has one root.
That's it. You don't need a database, you don't need a complex front end. You just need a tiny bit of code that says, when you get a post request on this URL, take the body of that request and do X with it. In Python, using FastAPI, that is literally 5 lines of code.
And X could be start a heavy AI process.
Right, and this is where the resource management gets tricky. If you are running your own server, you have to make sure that when X starts, it doesn't kill the listener. If your AI model suddenly grabs all the RAM and all the CPU, your web server might stop responding to new webhooks. This is the noisy neighbor problem, but inside your own server.
Oh, that's a good point. The listener is cheap when it's idle, but if it's the same process that then does the heavy lifting, you could accidentally lock yourself out. You'd be so busy thinking that you'd forget to listen.
Exactly. This is why in professional setups we usually decouple them. You have a producer and a consumer. The webhook listener is the producer. It receives the data and puts it into a queue, something like Redis, RabbitMQ, or even a simple disk-based queue. Then, a separate worker process watches that queue and does the heavy AI work.
So the webhook listener stays light and responsive no matter how busy the workers are. It just says, got it, and goes back to sleep.
Right. The listener's only job is to say, I got it, it's in the queue, here's a 200 OK status code. Bye. It takes milliseconds. This keeps the listening part of the pipeline incredibly stable and low resource. If Daniel is doing this on Modal, they handle all of that queuing and scaling for him behind the scenes.
This actually leads into a misconception I think a lot of people have. They think that being online is expensive, but being online is just having an IP address and a port open. It's the processing that's expensive.
It's the difference between having a phone in your pocket and actually being on a call. Having the phone in your pocket, waiting for a ring, uses a tiny bit of battery to stay connected to the tower. But the second you start talking, the screen turns on, the radio starts transmitting at full power, the processor is encoding your voice. That's when the battery starts to drain.
That's a perfect analogy. And just like a phone, modern servers are designed to be always on in that low power state.
Totally. In fact, modern CPUs have different C states. When the CPU is idle, like when our webhook listener is blocked and waiting, the CPU can actually power down parts of itself. It can lower its voltage and its frequency to save energy. It's on, but it's in a deep sleep. In 2026, server-grade CPUs are incredibly good at parking cores that aren't being used.
So even at the hardware level, the listening is optimized to be as close to off as possible, while still being able to wake up in microseconds.
Exactly. We've had decades of engineering dedicated to making this idle but ready state incredibly efficient. It is what allows your phone to last all day even though it is technically listening for notifications from a dozen different apps.
So, if Daniel wanted to get really granular, let's say you wanted to calculate the cost of just the listener part of his instance for a month. We're talking about what? Pennies?
If you look at the actual electricity used by a single idle process on a shared server, it's probably a fraction of a cent per month. The only reason we pay $5 a month for a VPS is for the guaranteed slice of resources, the IP address, and the physical space in the data center. The work of listening is virtually free.
That's fascinating. It really changes how you think about persistent infrastructure. It's not a heavy thing you're dragging along, it's more like a very thin thread you've left hanging in the air.
I like that. A thin thread. And as long as nobody pulls on it, it doesn't weigh anything. But the moment someone pulls on it, the moment that webhook is hit, it can trigger a whole cascade of events.
Okay, let's talk about some of the downstream implications of this. If webhooks are so cheap and efficient, why don't we use them for everything? Like, why do we still have polling at all? I still see apps that seem to refresh every 30 seconds.
Well, sometimes you don't have control over the sender. If you're waiting for a website to change and that website doesn't offer a webhook, you have no choice but to poll. You have to keep checking. Did it change? Did it change? It is a pull versus push problem.
Right, because you can't force them to buzz your room if they don't have a concierge.
Exactly. Webhooks require a push architecture. Both sides have to agree on the protocol, and there are some security implications too. When you open a webhook, you are essentially opening a door to your server. You have to make sure that only the right people can walk through it.
That's a great point. Let's talk about that. If I have this lightweight listener, how do I make sure it's not being abused? Because if it's always on, that means it's always a target for scanners and bots. Does the security part add a lot of resource overhead?
This is a real concern. Even if your listener is cheap to run, if a botnet starts hitting it with 1 million requests a second, it's going to get very expensive very fast, either in terms of bandwidth or CPU usage trying to reject those requests. This is where edge security comes in.
Edge security? Like living on the edge?
Sort of. It means moving the security check as close to the user as possible. Platforms like Cloudflare or Fastly sit in front of your server. They have massive capacity to absorb attacks. They check the requests, and if they look like garbage, they drop them before they ever reach your thin thread.
And if I'm doing it myself, what is the low-resource way to secure a webhook?
The most common way is using HMAC signatures. The senders say Daniel's voice form takes the data, mixes it with a secret key that only he and the server know, and creates a unique signature. The listener's first job, before it does anything else, is to run that same math. If the signatures match, the request is real.
And is that checking expensive?
It's a very fast mathematical operation. It takes a few microseconds. If the signature doesn't match, the listener just drops the connection immediately. It doesn't even wake up the rest of the application or start the AI pipeline.
So you can maintain your low-resource profile even under attack, as long as you can quickly identify the bad actors.
Right. And in 2026, we also use things like eBPF, Extended Berkeley Packet Filter. This is a way to run tiny sandbox programs inside the Linux kernel itself. You can actually write a security rule that drops unauthorized webhook requests before they even reach the socket layer. It is the ultimate in efficiency.
It's like having a security guard at the front gate of the hotel who checks IDs before they even get to the concierge.
Precisely. It's all about layers. The deeper the request gets into your system, the more expensive it is to handle.
So, to summarize the technical side for Daniel, the always-on nature of webhooks is possible because of the way modern operating systems handle network sockets. By using blocked processes and kernel-level event notifications like epoll and IOUring, we can have thousands of listeners that consume virtually no CPU and very little RAM. The actual cost is just the state of the connection and memory, which is tiny.
And the magic of it being free on serverless platforms is just a result of shared infrastructure. You aren't paying for your own waiter, you're sharing a very efficient front door with everyone else. The platform only charges you when they have to do the real work of running your code.
That is such a clear way to look at it. Now, what about the practical side? If Daniel, or any of our listeners, wants to set up their own persistent automation instance in 2026, what are some pro tips for keeping it efficient?
Number 1, use a lightweight language. If you're just catching webhooks, you don't need a heavy Java or Ruby environment. Go and Rust are the kings of this right now because they compile to small binaries and have incredible concurrency models. But even Python with Fast API is fine for most people.
And avoid the one thread per connection model.
Absolutely. That is the old school way. Make sure your server is using an asynchronous or event-driven architecture. In Python, that means using tasync and await. That's what allows the process to sleep efficiently while waiting for IDO.
What about keep alives? I've heard that term in networking. Does that affect the resource usage of a webhook?
Keep alives are more for when you have a connection that stays open, like a WebSocket or a database connection. For a standard webhook, it's usually a one-and-done request. The connection opens, the data is sent, and the connection closes. This is actually more efficient for the listener because it doesn't have to maintain any long-term state.
So it's even lighter than a persistent connection.
Much lighter. It's like a letter being dropped in a mailbox versus a phone call where you both stay on the line. Once the letter is in the box, the mailman is gone, and you can check the box whenever you want.
Okay, let's talk about the what-if scenario. What if Daniel wanted to run 1 million webhooks? Like, he becomes the next big automation platform. What changes then? Does the thin thread start to break?
Then you start hitting the limits of the operating system's file descriptor table. Every socket is a file, and Linux has a limit on how many files a single process can have open. You have to start tuning the kernel parameters, things like ulimit, to allow for millions of connections. This is the C10M problem, 10 million concurrent connections.
So the bottleneck isn't the CPU or the RAM, it's literally just the index of files the computer can keep track of.
At that scale, yes. You also have to worry about the epoll set size and the amount of kernel memory used for the TCP stack. But we are talking about extreme scale here. For an individual or a small business, you will never hit those limits. Your $5 VPS could probably handle every webhook Daniel will ever need in his entire life.
That's a very empowering thought. The technology is so efficient that it's almost free at the human scale. We often worry about the cost of tech, but in this one specific area, we've really won.
It really is. It's one of the few areas in computing where we've actually reached a sort of peak efficiency. We've gotten so good at waiting for data that the waiting part is basically solved. The only thing left to optimize is the doing part, which is why things like Modal and specialized AI hardware are so popular right now.
It's funny, we spend so much time talking about how to make AI faster, or how to process big data, but the waiting for data part is this quiet unsung hero of the internet. It's the silent foundation.
Without it, the real-time web simply wouldn't exist. We'd all be stuck in the polling dark ages, and our batteries would all be dead by noon. Imagine if your phone had to manually check every 30 seconds if you had a new WhatsApp message. It would be a disaster.
I think that's a great place to wrap up the technical deep dive. Daniel, I hope that sheds some light on why your automation pipeline feels so magic, and why it's so cheap to keep that first part of the instance running. It's all about the kernel doing the heavy lifting while your code gets to take a nap.
And if you ever do find yourself paying more than a few cents for a listener, you might want to check if you've accidentally left a while true loop running somewhere. That is the fastest way to turn a thin thread into a burning fuse.
Good advice, Herman. So, before we sign off, I want to give a quick shout out to everyone who's been listening. We've been doing this for over 600 episodes now, and it's still just as fun as it was on day one.
Maybe even more fun now that the tech is getting so weird. AI agents, serverless GPUs, persistent automation. It's a great time to be a nerd. I mean, we are literally talking about kernel interrupts on a sunny afternoon in Jerusalem. It doesn't get better than this.
It really doesn't. And hey, if you are enjoying the show, we'd really appreciate a quick review on your podcast app. It genuinely helps other people find us, and we love reading your feedback. It's like a little webhook of positivity hitting our server.
Yeah, it makes a huge difference. We're on Spotify, Apple Podcasts, and pretty much everywhere you get your audio fix. We even have a decentralized feed now for the Web3 crowd.
You can also find us at myweirdprompts.com. We've got the full archive there, plus a contact form if you want to send us a prompt like Daniel did. Or you can just email us directly at show@myweirdprompts.com. We read every single one.
We're always looking for new rabbit holes to dive into. The weirder, the better.
Alright, that's it for today. Thanks for joining us on this little journey into the world of webhooks, kernel interrupts, and the efficiency of doing nothing.
This has been My Weird Prompts. Until next time, keep your sockets open and your interrupts ready.
Bye, everyone.
Bye.
This episode was generated using Gemini Flash 3. Text-to-speech engine was Chatterbox.
Thanks for listening to another episode of My Weird Prompts, an AI-generated podcast featuring Daniel Rosehill's AI prompts, as answered by a revolving cast of friendly AI characters including me, Cornelius the Sloth. Subscribe on Spotify or visit myweirdprompts.com.